Uh, Morning, everyone. So I'm Zinedine. So I am in School of Mechanics at Leeds. So the call that the talk today is about how we can use a simple model to that will allow us to analyze a complex system, and using CFD-based data-driven application in the area of liquid extraction. So this is give you a bit of background. What's liquid extraction? Nowadays, we want everyone, for instance, the application nowadays, we want everyone to use electric batteries. Okay, but at some point, we'll have to reprocess, in order to recycle those critical materials. In the nuclear industry, for instance, we want to recycle, the food processing. So there are various systems that allow to do such system, and I've been working on pulse columns. There are some other centrifugal. So the focus here is about mixer settler. So the idea is to improve the performance, okay? And here we are dealing with multi-phase flow. So we have two flows. So the idea is to enhance the mixing of those two flows. You've got, let's say, a heavy phase coming and mixing with a light phase mixing, and the idea is to enhance this performance, to have a better efficiency. So the key parameters, okay, in terms of this mixer settler, you've got the operating conditions. I mean, how long, how fast, or how low, you will have those flow of those fluids, and which will affect, obviously, the flow patterns, of those very complex fluids, and geometric parameters, which actually will affect here how long it will take, for the flow to go in and out, which relates, to the residence time. So here in this, so we will obviously the idea is, you mentioned in your talk, he did some simulation multi-phase flow using VOV. It takes a long time, isn't it? So when I first look at that, and I say, well, I like to do something simple. As that's what I say to the students, use simple things. So I asked one of my students, trying to look into this using single phase flow. She came back to me and said, but I find it difficult to comprehend how we can actually represent multi-fluidic system with single phase flow. I say, well, just do your research and you will see. So the idea is to develop a very easy reduced order model, that will be able to infer an optimum design, which actually will have a higher, efficiency. So obviously there has been various people doing such similar work using multi-phase flow analysis. But actually, I haven't seen any formal CFD-based formal framework, optimization framework in this area. So the idea is to use open form facility. We'll combine that with a data-driven based methodology. So just in few words, so this is the kind of a settler that we are using. So we've got this body condition, we've got inlet, you've got various baffle. Okay, so the idea is to use steady state simulation using open form framework, simple form, and then also using scalar transport form, which allows us to develop the residence time distribution analysis. And then at the end, we'll do optimization, we mix all that. And something which is important to the design is this Pareto, okay, which should be important for the key design. So how we put all those things together? Oops, excuse me. So the assumption is, we are in the laminar regimes. Okay, so we have the unsteady laminar steady state Navier-Stokes equations for single phase flow, which is here. We do the various work that has to be done in terms of grid independence analysis, et cetera, et cetera. And then we found out that, using about 0.15 million elements is enough, okay? So we use automatic parallelizations, subdomain, in order to minimize the connection between all domains. So in terms of the residence time distribution, so what we do, the process, we do steady state simulation. So convergers. At the end, what do we have? We have a flow field, the velocity flow field. So the velocity flow field will be our input here. So here what we'll do, we'll have at the inlet here, we use the velocity field, we'll put some tracer, and you will see how long does it take, for the tracer from in and out at the aqueous outlet, okay? So the idea of using a residence time distribution, FT is the proportion of flow at a certain time, which is actually inside in the system. So once we have this, so for instance, so what we have here, we have as time t here. So we will have something like that. Okay, we put the tracer. Okay, and then so this one is f, and then what we'll do, we will differentiate. Okay, and then sometime we will have something like that. Okay, so this is the idea, and the idea for such system is to reach plug flow. Plug flow is you want obviously the flow to go as quickly as possible. So what idea is mathematically you want like a Dirac approximation. You want this actually LTD sigma t to be as peak as possible. You don't want it to be spread. Yes, so this is okay. So how do we formulate this optimization? So first of all, what are the design variables? The design variable here will be the position of the baffle position, this baffle. We'll move this baffle, okay? Then the flow rate. So we use those two design variables. So this is the range of the flow rate, and the baffle will change in from this 55 mil to, so this will move like that, okay? So what are the objectives? So we have a system. I think the idea is what to put minimum energy. And we also want to minimize the sigma t, the sigma t. So what do? We just generate, design of point within the space. Okay, so we use optimal Latin cube sampling. The idea of this is actually to minimize this energy, between each of the points in order to have another distribution. So you can see here we've got about 24 points, and then it's nicely distributed to represent the whole design space. So once we do simulation, we do that, we use a multi-objective general algorithm. And then in order to represent our meta model, we use radial basis function, especially using cubic. So here, these are the representations for the energy losses. So after we perform our all 20 simulation, so this is a function of the E losses. And here we have the sigma t. And the idea is to find the minimum, well, together. So if you look here individually, well, we can see that the regions of where the sigma t is minimum is around here. And for the energy losses, it's in this area. So the idea now is to minimize those two together. So in order to, before doing that, say, well, how do I know that, so I retrieve the pressure drop, and I retrieve my residence time. How do I know this is correct? How? So in terms of pressure drop, we evaluated that with the work of Neves and Shimada, and you can see that we have the similar power with the Reynolds number power law approximation, and it's it's actually quite nicely, fit the data. In terms of the, the other residence time, a very important number in this, in liquid extraction is the so-called dispersion number, which actually for a gravitational number is represented by the residence time divided by the square root of h and g. So h is the dispersion band, okay? So in order to evaluate this, I use a correlation by those guys, okay? From which the mixer settler has been developed, and I use this correlation by Zinedine and to represent my parity plot. This is all the set of data, and then you can see that it's nicely done. So this by using single phase flow simulation. Okay. So what is the idea? As I mentioned at the beginning, the idea is to have a nice Pareto front, which is very important for the design. Obviously, what the process is to validate. So how do I know that? So we take 7 points on the Pareto front, and then we can see that the percentage error between the CFD and the prediction of the data-driven model is between 5 and 6% for the two objective function. If you look at this curve, I would say which would be the optimum point? 0.4. Okay, 0.4 seems to be the the optimal point. Well, the best compromise, I should say, which is correspond to these values in terms of energy losses and sigma t. However, so let's look at those RTD analysis. What I mentioned earlier. So if you look at the Pareto front and those various RTD, ideally you say, I would like something like that. Okay, so but should be the point, which 0.7. Okay, if I look at 0.7, what does it mean? 0.7, okay, to be a good design, an increase of about over 200% in terms of energy losses compared to the point number 4. So when you design a system, obviously you want to use as minimum energy as possible. So I would say that number 7 is actually inappropriate. Okay, so it seems that 0.4, in my opinion, the analysis seems to be the best design. All right. So this is actually the flow pattern, very complex, even though this is single phase simulation. All right. And what might argue, but okay, Zinedine, it's good, but we're dealing with multi-phase flow. And I said, hold on a sec. So what we did some multi-phase flow analysis using both, and obviously it took much longer. And then the idea is to what? To look at the flow pattern. So here we've got the single phase analysis, but the path line colored by the velocity field. And you've got, look, what we want a nice plug flow, like go in and out. Okay? And if we use our multi-phase flow colored with the water fraction, we can see that, look here, we have this nice path, isn't it? And nice recirculation. So using this simplification of a framework, we were able to actually find out, the best flow pattern using minimum cost. So for a single phase simulation, it lasts about 15 minutes. For the scarless transformed form, it lasts about between 2 and 2.5 hours. So whereas, multi-phase flow for simulation is hours, if not days. And if you were to use large AD simulation to actually capture all the things, even worse. So I'm personally very pleased with the results. So to conclude, so we have successfully developed optimization framework for gravitational mixture settler. So obviously we have shown that we can improve, the performance of the system in terms of separation efficiency, and obviously flow rate and the buffer position are key design variables. And we the designer now, they have this Pareto front, that they could use, to have a range optimal solution. Okay. Thank you very much. Thanks a lot.